In this video, I want to have a look at more complex exponential growth and decay problems. So we did look at exponential growth and decay in the mathematics course, but in this one we want to look at it where it's a little bit more complex, where n has a rate of change that's proportional to the difference between n and p. So that looks something like this. So we've got the rate of change of n over time is equal to k times the difference between n and p, where k and p are just constants. And this is going to have a general solution that looks like this. N equals p plus ae to the kt, where a is a constant. So this part is the part that we've seen before. All right, so we can prove that that is the general solution. If we have n equals p plus ae to the kt, if we differentiate n with respect to t, our p is a constant, so that's just going to go to 0, and we would have to multiply down by that k, so we'd have k multiplied by ae to the kt. Now if we rearrange this, we could have k outside of p plus ae to the kt, because we're trying to get it to look like this. But if we add a p in there, then we have to compensate by that, by subtracting a p again. So that whole thing, this first bit is just n, so we'd have k outside of n minus p, which is what we wanted. So let's have a look at some examples. So in our first example, we're told that in a certain town, the growth rate in population is given by k outside of n minus 125. We're asked to show that this equation is a solution to this differential equation. So if we start just by writing out that equation, so 125 plus ae to the kt, we're going to go through the same process we just did when we proved it. So we're going to differentiate n with respect to t, which would give us k times ae to the kt. And if we put that in brackets, we can put our 125 in there, plus ae to the kt, and then compensate by minusing 125. And that's going to give us k outside of n minus 125. So that proves that it is a solution. For part B, we're given two pieces of information. So we're told the population is initially, so when t equals 0, the population is equal to 25,650. And we're told that when the population is after 5 years, the population is equal to 31,100. And we're asked to find the population after 8 years. So we can use these pieces of information in this equation to figure out the values of a and k. So first off, we're going to use this one. So we're going to have our 25,650 is equal to 125 plus ae to the kt, but t is 0, so that's just to the power of 0, which means that a would be equal to 25,650 minus our 125, so it's going to be equal to 25,525. So that means that our equation then is that n is equal to 125 plus 25,525 e to the kt, but we still need to find k, so that's where we use these ones. So if we substitute those values in, we're going to have 31,100 is equal to 125 plus 25,525 e to the 5k. Now we want to go through and rearrange all of that to make k the subject. So we're going to minus our 125. So we're going to have 30,975 equal to 25,525 e to the 5k. Now dividing both sides by this number here, we'd end up with just a 1.2 equals e to the 5k. Taking the natural log of both sides, I'd have 5k is equal to the natural log of 1.2, which means that k is equal to the natural log of 1.2 divided by 5. So that then tells me that my whole equation is going to be n equals 125 plus 25,525 e to the power of the natural log of 1.2 over 5t. Now the question actually asks us to find the population when t is equal to 8. So we're going to substitute that in. I'm not going to write all this out because I'm running out of room, but you should write in your substitution as well, especially if you're in an exam. And if you plug all of that with an 8 in there in your calculator, you're going to end up with 34,295.8, and it keeps going. Now, because we're talking about people, we haven't quite reached the 96 mark yet, so therefore our population is 34,295 people. For part C, we're asked to find when the population will reach 40,000, correct to 3 sig figs. So we're going to pop our 40,000 over here in our equation. So that's going to equal our 125. So this equation is just the one we figured out in the earlier parts of the question. And now we have to go through and solve it for t. So first I'm going to subtract my 125. So I'd end up with 39,875 is equal to 25,525e ln 1.2 over 5t. Now if I divide by that, so I'd have my 39,875 over 25,525 equals e to the power of ln 1.2 over 5t. Now I'm going to take the natural log of both sides, and that's going to give me ln 1.2 over 5t. And now I can divide each side by the ln 1.5 over 2, ln 1.2 over 5. So I'm going to have the natural log of this whole number here. And that whole thing is going to be divided by my natural log of 1.2 divided by 5. And if I work that out, it's going to give me 12.2336, and it keeps going. To 3 significant figures, we're therefore going to have 12.2 years. In our second equation, we're told that a saucepan of water is heated to 95 degrees, the room temperature is a constant 23 degrees, and the water cools down to 55 degrees after 5 minutes. The cooling rate is proportional to the difference in the water temperature and the room temperature. So before we even start looking at what the question's actually asking us, let's just pull out all the important pieces of information from there. So the room temperature is a constant 23 degrees, so that means our P is going to be 23. We're told that the water is heated to 95 degrees, so that means at T equals 0, the temperature is going to be equal to 95 degrees, and that after 5 minutes, the temperature is equal to 55 degrees. So these are all the pieces of information we can use. For part A, it asks us to show that the equation for the water temperature is given by this. Now this is slightly different to question 1. Question 1 gave us the equation and asked us to prove that it worked. This one is asking us to derive this equation. For part A, we're going to start with the temperature is equal to P plus A e to the kt, and we need to go through and figure out what all those things are. So we already figured out that the P has to be the room temperature, because that's what we're looking at the difference between. So we've got 23 plus A e to the kt. And now we can use these 2 different pieces of information that we were given to figure out A and K. So if we use our initial condition first, we've got 95 is equal to 23, that's a 25, 23 plus A e to the 0, which means that A is going to be equal to 95 minus 23, which would give us 72 degrees. So that means our equation, or 72, sorry, not degrees, our equation is going to be 23 plus 72 e to the kt. Now we can use this and sub in our second conditions. So we're going to have 55 is equal to 23 plus 72 e to the 5t. Now if we minus 23 from there, we're going to have 32 equals 72 e to the 5t. So then we'd have 32 divided by the 72, which would give us 4 over 9. So we'd have e to the 5t is equal to 4 over 9. Take the natural log of both sides, so we'll have 5t is equal to the natural log of 4 over 9, and then divide both sides by 5. If we approximate that, it's going to give us minus 0.162186 and so on, which gives us this number in here. So then we can say, therefore, t is equal to our 23 plus 72e to the minus 0.162t. So that's proved what it asked us to prove in the question, to derive that equation. Now, because it's given this equation with this t rounded off, we can use that rounded version in the next parts of the question. Part B asks us to find the temperature of the water after 30 minutes. So we're just going to substitute 30 into that equation there. So we'd have t equals 23 plus 72e to the minus 0.162 times 30. And if we pop that in, that's going to give us 23.558 and so on. So we can say, therefore, 23.6 degrees Celsius after 33 minutes. Part C asks us, when will the water temperature reach 30 degrees? So that's our temperature this time, so it goes in where the capital T was. And we'd have 23 plus 72e minus 0.162t, and we need to solve that for t. So subtracting the 23 first, we'd have 7 equals 72, e to the minus 0.162t. Dividing through, we'd have 7 over 72 equals e to the minus 0.162t. Natural log of both sides. And then dividing through, so we'd end up with t equals the natural log of 7 over 72, all divided by minus 0.162, which will give us 14.387 and so on. It asks us in this one to one decimal place, so we'll write therefore 14.4 minutes. For part D, it's asking us to show that the temperature of the water approaches 23 degrees as T approaches infinity. So that should say approaches, not approached. So if we're doing that, we're talking about a limit. So we want to take the limit as T approaches infinity of this equation. So our 23 plus 72e to the minus 0.162t. Now, if you think about just what this section here, that exponential, looks like in a graph, we know that it's an exponential coming down this way. So as t approaches infinity, this whole section here is going to approach 0, which means that entire second term is going to approach 0. So this whole limit is going to approach 23. So that's having a look at two examples of more complex exponential growth and decay questions.